Okay, this marker is not good. Okay, so just remember what we called this talk. This talk is and this marker is not good already. As a okay, this is based on 2 papers, and this marker also dead already. Browne from 2000, perhaps 9, and Raussendorf in 2013. So we want to think of a sort of device which computes something. What is a computation? So such a device, what should such a device do? Such a device should compute a function perhaps from a set of m input bits to a set of n outputs. And exactly what kinds of functions we can compute depends on what kind of computer we're using. Classical computer, quantum computer, something like this. So we can talk about a very simple linear computer, which computes some function. L goes from Bm to Bn, such that if I have a set of x, a vector x of inputs, like a bit string, x1 to xm, then this goes to some, L is some matrix, it's some, let's see, m by n matrix times x. So if it's a linear sort of computer, what can a linear computer do? It can add things together, basically, when you're doing Z mod 2. Here it's Boolean, yeah. Yeah. Yeah, so a common example that we have is going to be this XOR, which is a function from B2 to B1. So what does this do? So what does it do? It just adds together 2 bits. So this is one version of XOR. So the way that it works is that here L is just equal to 1, 1. And what you do is L times X is just something like 1, 1 times X1, X2. This is X1 plus X2. This is one example of such a map. So this is linear. So let's give an example of a map that we will use that's nonlinear. I mean, this is straightforward, but such a map could be something like you have x1, x2 going to like x dot y plus 1. In fact, this is the function NAND, because what's the truth table here? We have, if we have input x1, x2, and then we compute this function, 0, 0, 0, 1, 1, 0, 1, 1. Then what this computes is 1, 1, 1, 0, which this is the NAND function, which we will use shortly. Okay. So we want to just talk very quickly about, so let's talk about complexity in a very broad sort of way. So if I have a linear computer, what does this linear computer do? All it does is add things together, and so it solves efficiently complexity problems. All it can do is just add numbers together, do linear operations. So it solves problems in what's called some complexity class. It's not that important, so you'll get the idea of why I just want to introduce this notation. So we might want to ask the following question. If we have some sort of simple computer, such a simple computer cannot even compute most functions. It can just compute linear ones. It can't compute the NAND one, for example. So we might want to eventually ask the question, what resources promote a computer that computes just linear things? What resources promote plus L to other complexity classes like P or BQP? So this is the sorts of problems that can be solved efficiently by a classical computer. This is by a quantum computer. So what sorts of things do we need to add to this little linear computer so that it achieves some higher ability to... By class N? Sorry, I didn't get it. What do you mean by class N? It's a complexity class. All it is think of some problems that you can solve by just adding numbers together. There's a certain class of problems, and this computer can solve... Yes. Yeah. Parity L is what it's called. Yeah, it's a name, by the way. It's just a name, which linear computers can solve problems in this class, but it can't solve any problems that require you to compute nonlinear functions. Okay, so here's the question. What resources promote this parity L to other more higher classes, P and BQP? So there's this MBQC. This is the motivation for what we want to do, but so let's just remember what MBQC sort of looks like schematically. So imagine you have some linear control computer L, and then you have a bunch of qubits. These are like different parties, each doing different sorts of measurements at each site. So what the linear control computer does is it sends some input bit to tell you which measurement to do, and then you get it performs a measurement, gets an output, and sends it back to L, and it does this for all the different sites. And all L does is it takes those and then it maybe adds them up, and then based on what it adds up, it then tells another qubit what to measure or not to measure. This is all that's going on. And so in MBQC, we can sort of answer this possible question: what resources promote? So here we have a linear computer. All it does is add things up. And what we know is that there are certain quantum states, cluster states, such that if I have a cluster state, it takes me from this complexity class to quantum universal computation. We know this. So we can ask a similar question about this P. So we have the following fact: a polynomial supply of NAND gates. What do I mean by gates? Just I'm computing NAND functions. Allows for universal classical computations. So if we want to promote this parity L type of simple computer to classical universality, what we want is the following. What resources are such that if I have a resource, which I'm not defining, a resource, we're going to end up thinking of this as some sort of like a PR box or a quantum state or some empirical model. What empirical model allows you to go from parity L to P? So based on this fact, I know that if I have a bunch of NAND gates, I can compute any classical function that I want. This is what this says. So in order to go from parity L to P and solve, all I need to do is to promote these linear operations to non-linear operations. Need non. Okay. Okay, so okay. Okay, so let's consider, we're going to look at the quantum case, but everything can really be done in terms of probability tables, but some of the tables are coming from quantum mechanics, so let's just introduce some notation. So we want to consider a bipartite scenario, Alice and Bob, where we have that HI is C squared equals, and let's, okay, these are density matrices. One way to look at that is that these are eigenvalue, these are matrices on Hilbert space where the eigenvalues are non-negative. Okay, so this is a quantum state. And also, let's just define something that we'll need. So a computation F from Bm to Bn is deterministic. If it produces the same result with probability 1. Is determined if f of, I will just shorten this. It is determined if the outputs all computed with probability equals to 1. Okay, so I want to just say that, just some notation, let, I guess I will let L okay, so I want L to be the, so in the picture that I drew previously, L is the kind of computer that just adds numbers together. So so we have this result. This is Anders and Browne's result, which is the following: no bipartite quantum state rho can enable L to deterministically, so I will abbreviately compute the NAND function. So here's sort of a schematic, just a picture of how we're going to interpret this situation. So you have some computer L. So what does L do? L sends bits to Alice and Bob. So it could send input X to Alice, input Y to Bob, and they perform some sort of measurement. They get outcome A and outcome B. And of course, this is not a geometrical representation of what's going on, but then, so maybe they send it back this way, but just the idea is that then they return these bits to L, and what L does is maybe adds them together. A plus B or something. So what we want to say here is no bipartite quantum state can enable this device, this thing over here, to deterministically compute the NAND function. So basically, if I give, so what is the NAND function, right? So this was something from B2 to B1, and so over here we have two inputs, X and Y, and then you're going to perform some measurements on your quantum state. You're going to get outcomes A and B, and then when L sums them together, the theorem says it's not possible for any quantum state to deterministically compute that function. So at the end of this process, you're not always getting the truth table for NAND, right? Which was 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1, 0. We will not get this truth table with 100% accuracy. So the proof so just overall, let me just give you the basic idea. It follows from that quantum experiments have maximum CHSH value given by 2 square root of 2. So what do I mean by this? So the basic idea follows from the fact that what you're going to find is that this NAND gate that I wrote before, in order for this to be deterministically computed, you actually need a PR box. But PR boxes are not allowed by quantum mechanics. They're out of the quantum set of states. So actually, that's how the proof proceeds. You observe the fact, this is a fact due to, this is a theorem due to Cyrilson, that for any bipartite quantum state, the maximum CHSH value, maybe I'll write it here, CHSH is, for quantum states, is less than or equal to 2 square root of 2. This is a theorem due to Cyrilson. So the basic idea is show that. Yeah, so I will make it more, but by CHSH value, what do I mean? I mean this expectation is expectation of 0, 0 plus expectation of 0, 1 plus expectation of 1, 0 minus expectation of 1, 1 is this. There is this function, and this function, if it's classical, you know it's less than or equal to 2, right? This is the CHSH inequalities, but there's also a bound for the quantum mechanics, and this is the bound for quantum mechanics. But I'm going to show that to obtain this NAND gate for two parties, Alice and Bob, you need a PR box. But PR box, yeah, PR box has CHSH. It's 4. Yes, CHSH. Sorry, PR box gets a CHSH value of 4. Therefore, it's not. Therefore, no quantum state achieves this function for two parties. But we will show that for 3 parties, you can do this. No, right? It's the, maybe you're right. Is it 3? I think it's, plus or minus. By the way, the expectations, but it's minus -1. That's the minimum. When it's, yeah, that's right. It's minus -1. So you talk about something. It's like similar, but yeah, exactly. Yeah, if you're dealing with the probabilities, then the maximum is 3. Yeah, with probabilities, the maximum is 3. Okay, so let's just get into this real quick. So, okay, so suppose that we're given some inputs. We're given some x, y element of z 2 and a quantum state. What we want for each xy, we have a quantum state. We're going to perform. I think your phone just that. That's not possible. No, nothing. It gave some sort of weird message from my. Yeah. No, it should have battery for a while. Okay, so we're given a set of inputs. This tells me which measurements to perform, and then I want a set of outputs from this, such that the following holds. The probability with respect to a quantum state rho of A plus B. A is the outcome of Alice's measurement, B is the outcome of Bob's measurement, has to equal the NAND. I'm just going to abbreviate the NAND function for n of xy, given that I have input string xy, and this needs to be equal to 1. This is what it means to deterministically compute this function. Alice and Bob, they perform their measurement, they get outcome AB, and then the linear computer L, adds them together, and it deterministically computes the function if this is precisely equal to this output 100% of the time. So an example of this is, say we have xy equals 0, 0. Then what does this look like? I have this table of probabilities, P00, P01, P10, P11. A probability table coming to me from some experiment. This is, let this x be equal to 0, y equal to 0 for the inputs. Then this NAND function we know has value 1. So A plus B have to be equal to 1. So I have that this 0, 0, 0 plus 0 is 0. So these two, and 1 plus 1 equals 0 mod 2. So these have to be 0. So we have some alpha and 1 minus alpha, like this. This is what it means to deterministically compute. But this is, of course, it's coming from some quantum measurement, by the way. So we also know that if it's coming from quantum measurement, that there's also these additional properties that are obeyed, these non-signaling properties. I will get to that in a moment. So what is the probability of success? So how do I know that I've successfully computed this function? What's the probability of this success? Probability of success is equal to, I sum over all possible inputs, right? Because I want to compute this function for all possible inputs. The probability of getting these inputs, so this is the probability that this L just sends me the particular pair 0, 0, 0, 1, 1, 0, 1, 1 times one of these probabilities. A plus B equals n of x, y. Yeah, that's I mentioned that. It's, yeah, the NAND function. Yeah. Yeah, I just didn't want to write it every time. It's just that function, yes. Given x, y. Okay, and this should be equal to what? It should be equal to 1. So if I just give you a random pair of... The rightmost. Okay. Yes, I will write it. Okay. So probability of, I'll just write this as success equals sum xy p of xy rho a plus b equals, I will just write this as nxy given xy. So I'm just averaging, and this needs to be, can you still see this? This needs to be equal to 1.
We can't see the 1.
You can't see the 1? Okay, so we know that this is the line. Okay. Good. So this is what we want. I'm going to make an assumption that's standard. let's this just be some uniform distribution, 1 over 4. It just means that L is randomly giving me one of these bit pairs 0, 0, 0, 1, 1, 0, 1, 1. So P of xy equals 1/4. So then what I have is that the probability of success is equal to 1/4 sum xy p row a plus b equals nxy given xy equals 1. Or it's this whole thing equals this sum over xy, p row a plus b equals nxy given xy equals 4. I think you can see up to here. Okay, so this is actually this function right here, which I will show in a different color, is CHSH function. Normally, it's written a little bit differently, so we're going to rearrange some stuff and show that this is going to be, this function this right here is saying that the CHSH function is equal to some value, and that value will exceed 2√2. Okay. What's that? No. Yeah, I was actually you. Okay, so to see that this is the same thing as the CHSH function, so I just need to use a couple of identities. So we have this, for a given input string, we have the expectation, which is defined as follows: -1 to the a plus b. This is expectation value. It's the correlation between the two variables, which can take values plus or minus 1 depending on what a and b is. So I've just written that instead of -1 to the a, -1 to the b, I just wrote it as -1 a plus b. A and b are random variables. So row a, b given xy. What is this? This is just one of these tables that I had before. So when you compute this out, what do you get? This is going to be positive when a and b are both 0 or both 1, just whenever they're the same. So you get row 0, 0, xy plus row 1, 1, xy minus p row of 0, 1, xy plus p row 1, 0. So I want to define a different variable here, just to make my life a little bit easier. Actually, I'll just write it somewhere else because this is too small. So let's see, what did I call this? P bar or P plus of C is defined as being P row of A plus B equals C given xy. So I will not maybe go through all the steps, but using this fact, using the fact that P plus, when the outcome is 0, plus P plus, so this depends on xy. Maybe I should say this somewhere. Yes. P plus C of xy. So, oops, change this to P plus 0 xy plus P plus 1 xy equals 1. You can just see that that would be the case because when it's 0, it's these two terms. When it's 1, it's these two terms, and those add up to 1. So using that, you can show that, for example, that P plus 1 of xy, it's easier to work with ones because of the way that this NAND function is defined. Instead of the 0, 1, you can show that this is equal to 1/2 1 minus e of xy. So if we have this function that we talked about before, which was the sum of the probabilities, equals to 4 there, we have now, I'm going to define this as S is equal to P plus 1, 0, 0 plus P plus 1, 0, 1 plus P plus 1, 1, 0 minus, sorry, no, plus P plus 0, 1, 1. And this equals 4. Okay, so this is, and then we're just going to plug in this expression for each of them, and what you get is that you have instead that this equaling 4 is the same thing as P00 plus P01 plus E10 minus E11 equals 4, which, by the way, is greater than or equal to, or strictly, this is greater than 2 root 2. Therefore, whatever probability table gives me the NAND function, it must exceed the quantum bound. Therefore, there's no quantum state which deterministically computes this function. By the way, so this is just what is precisely the probability table which gets this? So these are the Popescu-Roerlich boxes, so PR. So we have this, we have all the different inputs when the input is, so we have x equals 0, x equals 1, y equals 0, y equals 1. So what was the definition here? We had zeros here, and then 0 here. So we know that we also, any real computer should also satisfy this no signaling condition. So if we try to compute this NAND function deterministically, we need something like this, 1 minus alpha. But because there's this no signaling, that means that this marginal has to be the same. So this is alpha 1 minus alpha. This one's also alpha. This one's 1 minus alpha. And then this one, this marginal, this should be alpha, and this would be 1 minus alpha. But then you have this condition that alpha here, 0 plus 1 minus alpha has to equal alpha. So then alpha equals 1/2, which is precisely a PR box, one of them. So the PR boxes are the ones that compute, for a bipartite scenario, they are the ones that compute this function. So for any two parties, you can actually, in the real world, actualize this NAND function because PR boxes are not physical. So we have this other theorem. So if it doesn't work for two parties, does it work for three parties? The 3-qubit GHZ state with Pauli measurements computes the okay, so let's see also. So what is this GHZ state? By the way, we are working with, just to remember, we are working with here three parties, means I have H is equal to H1 tensor, or I say H0, sorry, H0 tensor H1 tensor H2, where each HI is equal to C2. And so what is the GHZ state? This is 1 over the square root of 2, 0, 0. This is a particular version of it, minus 1, 1, 0.
Just for two, or you can put that for more?
You can do it with this one. You can also do it for more, for higher numbers of qubits. You can always do it because if three of them have this property, then you can always do it for just those three. So just a couple of facts. So let's say that we have some X element of a single copy of the Hilbert space C2, where X is some bit. Then let's remember what the Pauli operators do. The X Pauli operator acting on X, algebraically what it does is it gives me X plus 1. And if I act the Pauli Y on some input X, 0 or 1, what does it do? It gives me negative 1 to the X times I times, so I is the imaginary number I, times X plus 1. So why, I just want to recall these because I want to consider the following set of observables. I have Pauli, and I will make this more precise in a second. XXX, okay, X, Y, 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 X, Y, 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 X. say I have these observables where I use the notation that if I have k on the 0th factor, so this is some Hermitian matrix acting on the this part of the Hilbert space, tensored with m acting on the 1 copy, n is acting on the 2 copy, that I write this as k, m, n. So the order matters. It goes from 0 to 1 to 2. So here, xxx means the Pauli observable x acting on the first, second, and third copy, or the 0th, first, and second. Okay, so the statement is the following, that these are, that this state this state GHZ is an joint eigenstate of these operators. So that's the claim. So just, or the observation. That GHZ is an of OI. Okay, just as to give you one example of how this works, if I act XXX on GHZ, what's going to happen? If I act, every time I act an X by this property, it gives me X plus 1. So when I acted on this, so I act X on each copy of this. So if I act it here, it goes from 0 to 1. So when I act XXX on this one, I get 0 plus 1 is 1, 0 plus 1 is 1, 1 plus 1 is 0. So I get 1, 1, 0. And when I acted on this one, I get 0, 0, 1. But there's a minus sign. So this one is equal to minus GHZ. Similarly, for the other ones, you get just that y, x, sorry, other way around, x, y, y on GHZ is equal to negative GHZ y, x, y acting on GHZ equals minus GHZ, and y, y, x acting on GHZ equals positive GH. By the way, do I have any other markers left, I wonder? It's fine. I think that these are starting, this one's also starting to die. Okay, so just, we want to actually think of this in terms of, I don't know, this might be too thin, right? Yeah, it's kind of thin because this is brand new. I think probably, maybe all of them are brand new. Yeah, okay, they're nice, but too new, probably. All of these are new, I believe. This one might be okay. This one looks like it might be used. Anyway, I will try to make it legible. So I want to go from these eigenvalues to thinking in terms of the probability tables again, because that's going to be the more general way to proceed. So I want to just write down again those equations in a different way. X on GHZ. This is -1 to the 1 on GHZ. So everything that I had there before, wherever there's a minus sign, I want to replace it by a 1 because it'll be easier to just work in terms of zeros and ones. So something similar for the rest of them. The only one with outcome 0 is going to be the very last one, which maybe I will also write. So x equals -1 to the 0. So how can I interpret what's going on here? What is XXX? XXX is precisely the outcome that you get from taking measurement X on the first party, measurement X on the second party, measurement X on the third party. And what we have is that if we let something like we do something like, this is the operator, and this is which tensor factor it is, so which party. We give outcomes like AI, something like this. And let's consider also, we could perform this Y measurement, and when we do this, we call this BI. So what is it saying when I take this multiplication, and I always get, because this is a eigenstate, no matter what values I pick for these A's and B's, it must be that they add up to being 1 if I'm doing these X measurements, or 0 if I'm doing YYX. So let me just write that down. What does this look like? What I'm saying is this first equation looks something like A0 plus A1 plus A2 always equals 1. That's what I'm saying right here. I assign a value to X. This is the outcome to this measurement, outcome to this, outcome to this. And no matter what, no matter the outcome, I always have to get 1. Similarly for the other ones. And then this final one, what does this one look like? It's B0 plus B1 plus A2 equals 0. So now how do I write down my probability table? It turns out that if I do something like, I'm going to list the measurements that I do together here. I have X, 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 Y, 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 X, Y, 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 X. And I have the outcomes here, 0, 0, 0, 0, 0, 1, 0, 1, 0, 1, 0, 0, 1, 1, 0, 1, 0, 1, 0, 1, 1, 1, 1, 1. So I have 8 outcomes like this. So this first one, what it means is that I only get outcomes that sum up to 1. So if I have outcomes that sum up to 0, then it can't have any probability of occurring. So that means that this one has to have probability 0, and 1 plus 1 plus 0 is 0. 1 plus 0 plus 1 is 0. This one's also 0. And it turns out that these other ones are all 1/4. So the next 3 lines look exactly the same. And then this final one, because this one sums to 0, is I have zeros, the places that I had 1/4 before, and now I have 1/4 where I had 0 before. And so we can see that this actually does produce exactly the function that we want. So, by the way, we can see this right here. When I apply this measurement, 100% of the time, I will get the outcome 1. And for the others, I will also get outcome 1 100% of the time. I can also see, but I can see this more clearly here. Wherever there's a 1, I add up the quarters. With probability 1, this computes 1. With probability 1, this computes 1. With probability 1, this computes 1. With probability 1, this computes 0. So this does the NAND gate for me. You see this? Same, right? Where do I have probabilities here? Whenever these outcomes, whenever they sum to 1. So if I do this experiment and then I take these outcomes and I sum them, this is what the computer does. It sums them together. It will always get outcome 1 with 100% chance. So it computes this gate. By the way, this is also contextual. This probability distribution is contextual. You can see that because I have all these different values, A0 plus B1 plus B2, B0 plus A1 plus, I guess, B2. These are all in Z mod 2. So if I sum up all these equations, then I have 2 times everything on the left-hand side, but I have, oops, well, it still works. 1, 1, 1, 0. So you get actually that 0 equals 1, which is not the case. So that's how you get a contextuality proof here. Let's see, what time is it? 3:30. Okay, so I will just illustrate general setting. And this part is due to, I can write it here. This is Raussendorf's paper. So we have this thing which is an L2, so L2 MBQC. What does this thing consist of? If you know about Bell scenarios, it's kind of, I'm going to erase this, but it's kind of like N22 Bell scenarios. There's going to be N parties involved, but each of them can choose from 2 measurement inputs, 2 measurements, and each of the measurements have 2 outcomes. The difference is that there's some sort of causal order here, because if Alice performs a measurement and gets outcome A, then you can have B, this A, determine what measurement that Bob will do. So there's some more complication here. So we have N parties. So for every party, party K, we say that we have a measurement input QK. Raussendorf, yes. Mm-hmm. For every party and every input, for every party / input, we have that the outcome can be 0 or 1, just what I said before. So say I pick a particular set of inputs. So just for now, I'm not going to put anything there, but say I run an experiment once and I get a set of outcomes. I'm going to write this by S. So what is S? It's just a vector, a tuple of outcomes, one for each party. I'm not going to go on. Sorry, I will stay here for 1 second. So, and then we have this function, which goes from, so how many possible inputs are there? There's, you have something, add 2. So I have these functions. So something from this to the n to z2. And all I'm going to do here is I'm just adding, just parity. Just adding them up. This is the function that I want to compute. For every input, I'm going to compute this output once, and that's the output of my computation. So I'm going to continue. So we have also that, say I have some, for a set of inputs, this is a vector of inputs. So this is, I just give this to my computer. It's me as the user giving it to the computer. I don't have to, these don't have to determine the measurements that I perform. Chokish. So I don't have to perform just these measurements. I could instead let my measurements, right? Q I'm using for the measurement input. It could be something more complicated, like this. And I will explain in a second. What's going on here? So this is the part that tells me that if Alice performs a measurement and she gets an outcome, T is going to tell me whether Bob's measurement depends on that. Why? Let me explain. So here, this is just some general matrix that it's just something. It depends on the computation I want to do. And then T is a strictly lower triangular matrix. So what does that look like? So say I have 3 parties. So let's say n equals 3. Then it means that I have 0. It's strictly lower triangle. 0 on the diagonal, like this. And then I have maybe some values here, A, B, C, like this. What's going on here is that when I apply this on S, the 0 row here, what does this mean? This means that the first party, say Alice, nothing can affect their previous, their choice of measurement because there's no party coming before them. Here, the fact that there's only one element here means that Bob, the second person to go, the choice of Alice's outcome can affect. And then here, the third party, Charlie, both the outcomes of Alice and Bob, maybe perhaps this should be, I don't know, maybe these are just ones like this, something like this. So Bob's measurement will depend just on what Alice got. Charlie's measurement will depend on what Alice and Bob got. So yeah, exactly, something like this. So that's why you want it to be lower triangular. And then this Q is something arbitrary, I think. I think you could just, for simplicity, if you thought of this as being the identity, you wouldn't lose too much. You obviously can't compute all the different stuff maybe, but just for simplicity, maybe you can think like this. Because I don't have a precise, okay. By the way, just if we pick a particular sort of MBQC where this t is equal to 0, this means that there's no causal order, everything is flat. So you just have that, and maybe if you just take Q equal to the identity, then, and you say N equals to 2 parties, then this is just the CHSH scenario, because yeah, there's no sort of adaptivity going on, so this is just CHSH. Okay, so this was a reading seminar where we have already introduced the sheaf theoretic approach, but I'm just going to write down some definitions because perhaps, let me think for a second. Maybe it would be good to just write down the result we want to work towards. Okay, no, let me just write some stuff down. Set of measurements. So if we have a function that takes me from a set of x is a total set of our measurements. So in the CHSH scenario, there's 4 possible 2 inputs for both Alice and Bob. So we can also talk about if we have some u, which is a subset of x, then a function from u to z2 is called section. And the reason we want to just make sure that we talk about the sections very quickly is because we want to connect to strong contextuality and computation. So to define strong contextuality, we need to have an idea of what a section is. What is this? This is just assigning to, if I have a subset of my measurements, this is going to assign a value to each of those measurements. By the way, if you have a context, which is something like x, y, or yx or something like this, then for each context, I obviously define a section, which is just the outcomes when I perform those specific measurements. So a global section is a function from the set of all measurements to Z2. When we have the CHSH scenario, we have 4 possible measurements, x, x1, xi, and yj. And a global section is just for each of these measurements. For Alice and Bob, you get some value ai bj. So there's how many global sections? There's 2 to the number of measurements, so 2 to the 4th, 16. So for CHSH, or maybe I write it here, 16 equals 2 to the 4th global section. Okay, so without going into, I don't want to redefine all of sheaf theory. So what I will do is the following. I will just define an empirical model, which we should know, but I will just remind. So what is this? This is a set of probability distributions for each context, right? A context is just a set of jointly measurable observables. These are, C is some subset of X, and M consists of sets of contexts, something like this. So what is an empirical model? This is a little distribution on every context for every possible context. And of course, they have to be compatible, like no signaling. Okay, so finally, we will define strong contextuality. So, or the support of an empirical model is precisely those sets of outcomes. So, let's say something like all global sections such that when you have a probability for a context and you restrict this section to that context, then that probability is zero, or sorry, greater than zero for every C element of M. So two examples. If I have, so yes, example, if I have, for example, a deterministic distribution, 1, 1, 1, 1, and everywhere else 0 in the CHSH scenario, and I have just one global section that is in the support, and that's the section S goes from X to Z2, where I have every measurement go to 0. Xi goes to 0, Yj goes to 0. Or maybe the notation I was using is Q, K for each party, I for each. So every single one of them is going to 0. That's the support of this. If you go to any other global assignment, you will find it's not in the support. For example, E is the contextual if we have that S of E okay. Just one more example. When does this hold? What? Oh, this is the empty set, right? Yeah. Yeah. So this? It's not empty. There's something in it. No, you're right. I wasn't actually sure. Yes. I will just say I don't know. Something about just that 0 looks ugly to me, so I didn't like it. Okay, yeah. So an example of something that's strongly contextual is the PR box. Okay, I will just show that one of these is not in the support. So the same function that we had before, x to z2, where you have each of the inputs going mapped, each ki mapped to 0. Is this in the support? How does this work? When I go to Q10, Q11, Q20, Q21. Okay, so how does this work? When I go here, I restrict to the subset of sections that are valid for this. So that's the point 0, 0, because I have zeros here. So on 0, 0, this is positive. 0, 0 in this one, also positive. 0, 0 here, also positive, but this one it's not. And then you can do this for all the 16 global sections. You see that this PR box does not have any. So you have that PR box is strongly contextual. Okay, finally, we have this theorem, which I think I will probably not prove, but I can talk about how to prove it. So this is and it's the following. Let M be an L2 MBQC that deterministically computes a vector O of Boolean functions on each input I. So here's the thing. If we have that O of I is nonlinear, then it must be that our model is strongly contextual. Okay, if you have an MBQC that deterministically computes some function, and that function is nonlinear, then it must mean that that empirical model is strongly contextual. So I just want to state two things before I'm just going to end it there. So I'm going to sketch the proof just quickly. So I believe that they use the following assumption. Which I also saw. There's, by the way, there's another paper. I will write it up here. Abramsky, maybe 2017. Abramsky and some collaborators. It has to do with the non-contextual fraction. They also do a similar theorem in here using the, they refine Raussendorf's theorem actually. But they also make the following assumption, which is that if M deterministically computes a function. Then it is either A, strongly contextual, or B, Raussendorf says this because he says that basically if it's not strongly contextual, then he says it must be that there exists a hidden variable model, which means that he goes straight to the classical case. So I'm not sure that this is true. If M deterministically computes a function, then it is either strongly contextual or classical. I think that this is something kind of strong, but it seems to hold true for many of the cases that we know about. And the following observation is important, that if you want for deterministic computation, consider the case, you want to prove it by saying first consider that you want to deterministically compute a function and that it's not strongly contextual. Begin with this statement. So if you want to for a deterministic computation, and you're saying that it's not strongly contextual, then you're going to the classical case. But if you want it to be deterministic, for deterministic computation, it suffices to analyze the deterministic distributions. Based on this assumption, it's either strongly contextual or it's classical. But if you want deterministic computations for every output, then it suffices to just consider the deterministic distributions. And when you look at deterministic distributions, what you have is something like the following. If you have a deterministic distribution, you have, so I'm just going to give you a sort of hand-waving strategy. The basic idea is this. When I have a deterministic distribution, I have a set of inputs labeled by parties and which measurement I do, and I map this to some value a k I. This is a linear map. For example, this could take value 0 or 1. This could take value 0 or 1. So you're going 0 to 0, or you have 0 to 1, 1 to 0. All of these possible maps are linear. And then, so if you do a linear map for each party and each measurement outcome, then the function that you're computing is linear. It's deterministic, but you can only compute linear functions with this because each assignment of values is itself linear. So that's the crux of the idea. The basic thing is that once you recognize that you have a deterministic distribution and the only way to assign values in this computation is to go from qik to some a. This is 0 to 0, 0 to 1, 1 to 0, 1 to 1. These are all linear functions. And once you do this, you can write that the output function is something like, it's something linear, maybe like it's like the diagonal of some matrix times the outcomes plus some offset vector C. It's something linear. And then, so Raussendorf goes on to do some more work to make it more precise, but the essential crux of the theorem is this assumption. And then if you want deterministic computations, you look at the best way of achieving those is the deterministic distributions, but these are just linear maps, and you have n of them, one for each, or not necessarily n. You have one for each measurement. These are all linear on each map, so the best you can do is a linear map. If that means, so if you assume that it's if it's not strongly contextual, it can only perform linear maps. Together with this assumption, it means that you can perform nonlinear functions only when it's strongly contextual, and there's no global maps like this. Yeah, and that's the basic idea of this one. Then there's a probability. So this is for deterministic computations. There is a generalization to probabilistic case, which I will not discuss. Probabilistic, yeah. In that case, it depends on, so in that case, what's the idea? An empirical model can be given in terms of alpha times contextual plus 1 minus alpha times non-contextual part. And then actually the better theorem is due to Abramsky et al., where they relate the probability of successfully computing this function to the non-contextual fraction. Yeah, so, and it reproduces this in the deterministic case. Okay, exactly on time.